Hello there, Mr. Sutton here, bringing you this lesson on the direct comparison test. In this one, we're going to be using the direct comparison test to determine convergence of a series. We're going to start this one off by deriving something called the direct comparison test. So let's say we have two series, both of them with nth terms that are greater than or equal to 0. See if you can fill in the following blanks. So let's say that A is less than or equal to B. If the series with B converges, what does that mean about the series with A? And once you've filled in that blank, the next one, let's say that A is greater than B. And let's say that now the series with B diverges. What does that mean about the series that has A in it? All right, so for this first one, if A is smaller than B and B is converging, well, if that means A is smaller than a converging series, which means it must also be converging. And by the same token, if A is bigger than a series that is diverging, A must be diverging. So this is the essence of the direct comparison test. So this is pretty useful if our series is either less than a converging series, like this first example, or greater than a diverging series, like this second one. Unfortunately, it doesn't really tell us much of use if our series is less than a diverging series. I mean, it could still be diverging or not. Or if it's greater than a converging series, it could either be another converging series or a diverging one. So in either case, you might have noticed that we have to have positive series. And the reason we need positive functions is that let's say we had a series that was diverging to negative infinity, that would actually fool the test and show up as less than a converging series. So we don't want that. Now the big question is, when is this going to be useful? To see comparison in action, we're going to check out this example. So if you take a look at 4 over radical n minus 2, this is almost a p-series, but it's not quite there. So we can't use the p-series test to really prove convergence or divergence for this thing. However, comparison is a good thing to try when a series is close to a series that we already know. So when you see one of these almost kind of situations, it's good to pick a comparison series, and we're going to be picking a series that's easy to determine convergence for. So for example, a geometric or a p-series, something like a one-step kind of problem. We also want to pick a series that's easy to compare nth terms with the original, because we're going to need to show that our comparison series is either bigger or smaller than this original, depending on what direction we want to prove. So a good series on this one would be 1 over the square root of n. It's easy to figure out convergence for, and it's also pretty easy to compare with the original because it's so similar. All right, so next step, and there's actually two steps that we're going to do. One is to prove that our comparison series converges or diverges. Another is to show that our series is either greater than or less than the original. It doesn't really matter what order you do these in, but I always like to do the convergence divergence first, so I kind of know what direction I'm trying to show with the inequalities. So this is a p-series that we just picked for comparison. P-value of 1/2, and since that's less than or equal to 1, we can very quickly show this diverges by our p-series test. All right, so next we're going to show that our series that we just picked is either less than or greater than the original, and that both series are greater than or equal to 0, are non-negative. So since our series diverges, we want to show that our series is less than the original, because if you have something that's bigger than a diverging series, you can conclusively show with direct comparison that your series diverges. So taking a look at this here, 1 over n, that is a denominator that is bigger than the original. This minus 2 is making this original denominator smaller. Bigger denominator means smaller overall fraction. And if you look in the numerator, 1 is smaller than 4. So overall, then, our fraction is going to be smaller for our comparison series. So we want to write our comparison series is less than or equal to the original. Again, we also want to make sure we show that both of them are bigger than or equal to 0. So a good way to do this is to show all three things, 0 in your two series, in one big inequality string. So I'm going to write 0 less than or equal to 1 over radical n, because that's the smaller of the two series. And then we'll write that 1 over radical n is less than or equal to my original, 4 over radical n minus 2. So I've shown that both series are positive, and also that my my diverging series is smaller than my original series in one shot. Next thing we're going to do, and by the way, before we take this next step, you also want to make sure that you specify what the n values are, because some n values are actually going to make this not true. For example, if you plug in 1 for n, square root of 1 minus 2 is actually a negative number, which is not bigger than 0. So you're going to want to restrict your inequality every single time to an n value you know is going to make it true. For example, if you have an n value of 3, greater than or equal to 9, I should say, so 3 minus 2, that's going to make this inequality true. But you could pick any n value, like 100, if you really wanted to, as long as it makes this true. So now that we've restricted that, all we have to do is write the conclusion. Since our original series is bigger than a diverging series, we just proved diverges, that means our original series must diverge by the direct comparison test. Here's another example to try out. Pause the video and see if you can get this one started. After you pick a comparison series, we'll bring it back together. All right, so on this one, we know that comparison is going to be a good shot on this one because really nothing else is going to work. Not even integral test is going to work all that nicely with this factorial. So let's pick something that's easy to figure out convergence for, that is similar enough to this that we can compare it. Now, it's good to start with kind of the end in mind. Like, I know that this thing is going to converge just because n factorial is such a huge, fast-growing function. I just need to prove it. So I'm going to pick something else that I know converges. Now, I could pick 1 over n factorial and compare that, but figuring out 1 over n factorial is going to be kind of a pain. I'm going to need the ratio test. So I'm going to pick something easier, such as 1 over n squared. Doesn't look very similar to n factorial, but we can still compare it, and definitely easier to find convergence for. I mean, this is a p-series with a p-value of 2, which we know since that's greater than 1, this is going to converge. So now we just have to compare this. What's going to be bigger as n grows to infinity? Our original series or 1 over n squared? Well, n squared grows a lot more slowly than n factorial. So that means that this denominator down here, since it's growing so fast, is going to make this fraction smaller than our comparison series. So I'm going to write 0 less than or equal to my original series, less than or equal to my comparison series. This is the order we're going in. But now we have to pick an n value where this is actually true. If we use the n value 1, we've got 1 plus 0 essentially, less than or equal to 1 over 1 squared. That is true. It's equal to it. But now if we go to even 2, this is going to be 1 over 2 factorial plus something that's a little bit less than 1 versus 1 over 4. This is going to be a smaller denominator over here with an n value of 2, which is going to make it a bigger fraction, which we don't want. So I'm going to go all the way to the n value 4. 4 factorial is 24. That gives me a larger denominator than 4 squared, 16, so I can start at 4. Again, if you wanted to be on the safe side, you could pick any n value you want as long as it makes this true. So you could start at n greater than or equal to 1,000,000, and on a free response, they would have to accept that, because eventually this series is going to be smaller than this other series. All right, so since we've shown that we have a series that is smaller than a converging series, that means by the direct comparison test, our original series also converges. For this last example, we're going to try to figure out whether this series converges absolutely, conditionally, or not at all. Pause the video and see where you can go with this one. All right, now the key on this one is recognizing that cosine of pi n is really just negative 1 to the n. You're just going back and forth between negative and positive 1 as you go to 1 pi, 2 pi, 3 pi on the unit circle. So I'm going to rewrite it like so. So it's now an alternating series. And if I'm testing absolute convergence, and I always test that first on these, I'm going to test this without the alternating to see if I can get it to converge without flipping back and forth. So that gives us e to the n over pi to the n plus 1. Now this is almost a geometric series, so close except for this little plus 1. So I'm thinking if I use comparison, I can get this thing to converge, because e is less than pi, so that would give us a common ratio of less than 1. But I have to prove it. So let me pick a comparison series that's pretty close. I'm going to go with e to the n over pi to the n, which I can also write as just e over pi to the n. Now this is a geometric series, has a common ratio of pi over, or e over pi. Since e is less than pi, that means this is a number that is less than 1. So this is going to converge for my comparison series. Next, what's smaller, my original series or the comparison series? Well, the only difference is that my original, we're adding stuff in the denominator, which means I have a bigger denominator and a smaller overall number. So that means that I can write 0 less than or equal to my original series, less than or equal to e over pi to the n. And now let's make sure we pick an n value that works. Since the only difference is that I'm adding 1 in the denominator, that means that immediately this term, this expression here, is going to be smaller than this other expression. So this is going to work for n greater than or equal to 1. Since I have a series that is smaller than a converging series, that means my original series must converge. And talking about absolute convergence, since I did this without alternating, that means that this series converges absolutely by the direct comparison test. So that's it for this one. Hopefully you see that when you have a series that is almost there, the direct comparison test has absolutely no comparison. Till next time, Mr. Sutton signing off.